So the first question says, Pine Forest High School reported that the senior class, 2.7% of the members are in Ski Club, 7.8% are enrolled in AP Calculus, and 1.6% are in both. So this is a great time to draw a two-way table. So we'll do one with probabilities. Just a reminder, two-way tables, usually 4x4 unless we have multiple categories. So I'm going to put a 1 down here. We're going to do S and not S, and C and not C. So we're going to start filling in the information. It says 2.7% of the members are in Ski Club. So that's 0.027 here. It says that 7.8%, so 0.078 in AP Calculus, and then 0.016 are in both. We want to find the probability of C given S, okay? So actually, when we look at this, we have given S. We don't even need to fill out the whole table, okay? So we're just going to do that one because we have given S. So we can find the probability of C given S by doing 0.016 over 0.027, which is going to come out to 0.5926. Now, we don't usually report probabilities as percents, but this problem happens to say to do that. So to the nearest tenth of a percent, make sure you do tenth of a percent. So we're going to move it over 2 and then round it to the nearest tenth is 59.3%. The principal would like a basic interpretation of these results. Write a statement relating your calculated probability to student enrollment in the given situation. So this is really just calculated probability, not probabilities. So that's A. Here's B. So we need to explain what does a given mean in this situation. So if we know someone is in Ski Club, there is a 59.3% chance they are in AP Calc. Okay, so that's an explanation of our given. I didn't actually use the word given. If you had to, that would be fine, just as long as you know you wrote that out. In a random sample of 250 men in the United States, aged 21 or older, 139 are married. The graph below simulated samples of 250 men 200 times, assuming that 139 of the men were married. So assuming that this is the actual statistic, 139 out of 250, this is what happened when we took random samples. Based on the simulation, create an interval of which the middle 95% of the number of married men may fall. Now remember, we could cut dots off the sides, which would involve multiplying the 200 by 0.025. So that would end up cutting about 5 dots off each side, okay? But we know when we have this information, that's the better, more accurate way to do this. So we're going to use our mean plus or minus 2 standard deviations. So 138.905 plus or minus 2 times 7.950. And if I type that in my calculator to the nearest integer, that's going to give me between 122 and 154 people I would expect if I took another sample of 200 people. Or another sample of 250 people, right? That's the sample size. We did it 200 times. Another sample of 250 men, I would expect 122 to 154 of them to be married. A study claims 50% of men 21 and older in the United States are married. Do your results from Part A contradict this claim? So I am going to see what would happen if I take 50% of the sample. So 0.50 is 50% of 250, and that would give me 125 men. So that 50% does fall in the confidence interval. So 125 falls within the 95% confidence interval. So this is not a contradiction. The scores on a standardized test that Jeremy took were normally distributed with a mean of 82 and a standard deviation of 5. On the test, Jeremy scored a 90. What percent of students scored better than Jeremy on this test? So this one's a little tricky because it doesn't say the word probability, but we need to use our norm CDF, and we can think about it as like, what is the probability someone scored at least as well as he did? So my min is going to be 90. My max is going to be E99, because we're going to go up to infinity, even though that's not a possible score on the test. My mean for the test is 82. My standard deviation is 5. So he did pretty well compared to the average. So we don't expect this value to be very big. But to the nearest tenth of a percent, we do get 5.5% for that, coming from a decimal 0.055. And specifically, just so you can check a little better, 0.0548 is what you would get and then round. The last question says, if Lisa took the same test at a different time and the scores were again normally distributed with a mean now of 83 and a standard deviation of 6.4, then what score to the nearest integer would make her percentile rank the same as Jeremy's? This is a little beyond what we did in class, but I wanted to put one on the review. So the way we can compare them is with their z-scores. So I'm going to find a z-score for Lisa. A z-score for Jeremy. So Jeremy's value was 90. My z-score is value minus mean over standard deviation. So I'm going to do 90 minus 82 using his information up here over 5. That gives me a z-score for him of 1.6. So I want her to have the same z-score so that she's at the same spot on the normal curve as him. So for Lisa, we want to say what score minus her mean is 83 over 6.4 is also going to equal 1.6. So she would be relatively ranked the same way. If we cross multiply and we solve this, we're going to get 10.24 from this equals x minus 83, and if we add it over, that means she would have to score a 93, it looks like, okay? If we round to the nearest integer to be equivalently ranked, and that's because on her test, people had a higher average, just 1 point, but the standard deviation was bigger, so she's gonna have to do a little better to be at that same spot.